Hi guys, and welcome to our last section of Area Study 1 Unit 4. We are going to be looking at chronic adaptations to training. So first of all, you need to understand what is a chronic adaptation and how it differs from an acute response. So the word chronic means long-term. So we are talking about a long-term change that happens within the body as a direct response to training. Now, these changes or these adaptations will go away once training is stopped, but these are changes that physiologically happen within the muscular, respiratory, and the cardiovascular system to make the athlete fitter, either aerobically or stronger or faster, and we need to understand what are the changes that happen in each one of these systems. So here we see some just nice little visuals. So first of all, it's important to understand what training methods will lead to different types of adaptations. So this slide is showing us that we have several different anaerobic types of training, whether it's plyometrics, whether it's resistance or weight training, interval training that's short or intermediate in duration, circuit training, that high work to rest ratio, or sprint training, and then versus aerobic training where we would be likely to get aerobic benefits from, such as the continuous fartlek interval circuit that's working at a low work to rest ratio and flexibility. So we're going to go through each one of the systems and each one of the adaptations that you need to know. So there are several definitions that you have hopefully retained from the acute response section in Unit 3, but I'll go over them again and how these differ as a chronic adaptation, so a long-term change. So first of all, in the cardiovascular system, we see that athletes who have taken part in any form of aerobic training will have a larger left ventricle chamber. Now that means that they're going to have a greater stroke volume and the greater ability to pump more blood out of the heart per beat. So the actual adaptation that you see is generally athletes will have a lower resting heart rate than somebody who is untrained. We then see an increased capillarization of the heart. Now the heart is a muscle itself and it needs its own blood supply. When someone trains, specifically aerobically, they'll have an increase in blood networks, an increase in capillaries that feed the heart. Therefore, the heart muscle is actually able to get more oxygen and therefore it can become more efficient and work harder. We see an increase in stroke volume. So the increase in stroke volume is a direct result of that increase in chamber size. And that thus it reduces the resting and the submax heart rate. We see an improved heart rate recovery rates, and that's due to increase in stroke volume. We see an increase in cardiac output at maximal workloads. Now that's not because that's not because heart rate increases. Specifically, if you have two athletes of the same age, their maximal heart rate should be about the same, but the difference is actually due to the increase in stroke volume itself. Here we see a visual. Notice that we've got an enlarged left ventricle, therefore this person's heart is more superior, more efficient. Now this picture here is showing something slightly different. This is showing us cardiac hypertrophy. So what I want you to notice here is that with the anaerobically trained athlete, so this is someone who's doing anaerobic work versus aerobic work, that they've actually got a thickening of the wall of the left ventricle. So because there is more muscle tissue around that ventricle chamber, they're going to have a much greater cardiac, a much greater contraction of the heart. Therefore, you're going to see with someone who's anaerobically trained, their blood pressure will increase quite considerably when they're doing strength-based work. And that's because of this chronic adaptation, which is the increased thickening of the left ventricle wall, versus someone who's aerobically trained who actually has a bigger chamber. So you need to have a think about the reasons why. So we see that we've got a bigger chamber because for someone who's aerobically trained, because their prime purpose or what they're trying to do is to be able to pump more oxygen from the heart. Versus someone who's got an increased thickening of the wall, it's all got to do with the force of the contraction and being able to pump the blood to the muscles at the fastest rate. We then see in this picture we've got increased capillarization. You can quite clearly see that there. And take your time to pause these slides and see if you can actually work out this equation, so the before and after. Having a look at this graph, it's important that you understand the key differences between someone who's trained and untrained. So someone who's trained, they start with a lower resting heart rate. They spend less time in an oxygen deficit. They reach their steady state much quicker, where oxygen supply meets oxygen demand. And then we also see that they've got a much lower and smaller epoch. Okay, and that's all got to do with the fact that they're using oxygen more efficiently in their body. We also see changes in someone's lactate threshold, or their lip. So we see that for someone who is trained, their lip is delayed, and that's got to do with the fact that they're going to be able to work at a faster rate for a longer duration aerobically than somebody who is less trained. So someone who is a more superior aerobic athlete will actually be able to work or run at a much higher intensity. Their speed, or their running speed, will be much faster, while still being able to be predominantly working aerobically with much less reliance on the anaerobic glycolysis system. And remember, it's the increasing reliance on the anaerobic glycolysis system that causes someone to tip over in their lip. So someone who's able to work more aerobically, they will have a lower lactate accumulation, and they'll be able to remove the lactate at a fast rate, therefore being able to remove it at a fast rate and being able to keep that final balance point quite low. Remember, the definition of lip is the last point where entry into and removal from the blood is balanced, and we are referring to the lactate. We also see that for someone who is more trained, they have increased plasma, they've got increased blood volume, increased hemoglobin levels. So hemoglobin is the oxygen carrying protein in your blood. So think of these like little buses. So someone who's a more superior aerobic athlete, they'll have more buses shuttling oxygen around their body. And that's got to do with a hormone called EPO. So EPO is a hormone that's produced in the kidneys, and it's produced as a result of aerobic training. So when the body recognizes that the athlete's body is under stress and that they need more oxygen, they stimulate the production of EPO, and EPO helps to produce red blood cells. So the more EPO that's released, the more red blood cells, the more oxygen that can be carried around the body, and the more aerobic work that can be done. We also see that somebody who is training will have a lower resting blood pressure. Now, this is really important to note because as an acute response, when we start to exercise, our blood pressure does increase. However, as a result of training, that chronic adaptation, when you do a training program, your blood pressure, your systolic pressure should go down. And that's because when you exercise, through repeated stress you're placing on the body, you're promoting the health of those blood vessels, keeping them nice and supple and flexible, and therefore at resting levels, your blood pressure will actually be lower. And that's got lots of health benefits for someone in terms of preventing cardiovascular disease. And that's a direct result of the fact that we've got increased capillarization of the heart, so the heart's receiving more blood. We've got improved elasticity of the blood vessels through repeated exercise. And then we also have an increase in HDLs, which they're the high density lipoproteins. They're the good forms of cholesterol that help to break the bad cholesterol that causes the clogging of the arteries and puts high amounts of stress on the heart. So increased when we train as an acute response, we actually see a decrease in blood pressure. Moving on to the next system is the respiratory training adaptations. Once again, there are few, and these all have to do with your increasing your body's ability to take in more oxygen. So we see an increase in tidal volume, the amount of air being able to be inspired and expired, and that's because the lungs actually increase in size, or their ability to take in more oxygen. That we have an improved lung function, and that's got to do with, once again, with improved lung volume and alveoli capacity. We also see that there's greater amounts or a greater ability to diffuse oxygen across the alveoli capillary interface. So more oxygen's moving into the muscles, and in reverse, more carbon dioxide is able to get removed out. So we see someone is able to have a much higher aerobic capacity because of this. And lastly, we're looking at the muscular training adaptations. So first of all, it's really important that you understand the difference between aerobic and anaerobic training in terms of muscular training. So when we're training aerobically, we're mainly targeting our slow twitch fibers, our type 1 fibers, versus anaerobic, which is our type 2 fibers. Now, the fiber type that someone's personal fiber type is made up largely by genetics and the types of training that they've been doing. And it's important that you understand that while you are generally born with a certain amount of fibers, you can actually train them to act more like the other. So first of all, we're going to go through aerobic training adaptations in the muscular system. Now, it's important that you understand the increased AVO2 difference, while as an acute response, it belonged in the cardiovascular camp. As a muscular adaptation, it belongs in the muscular camp. And that's because the reason why we see large differences between oxygen concentration in the arteries and the veins is because the muscles are actually able to extract more oxygen. And that's got to do with the fact that inside the muscle, we have more mitochondria. Which means that the oxygen powerhouses, we've got more of them, so they've got more sites to do aerobic ATP resynthesis. So more mitochondria, both the size, the number, and the surface area increases. We also have greater amounts of myoglobin. We also have greater amounts of a glycolytic enzyme. So that all put together, that enables the muscles to pull out greater amounts of oxygen when you're training. Some of the other aerobic adaptations that we see, I've gone through the first few. We see increased capillarization or density to the slow twitch fibers. So we've got more capillaries actually feeding the muscles, therefore greater amounts of diffusion that can occur. Our muscles get better at utilizing fats at submaximal levels. We call this glycogen sparing. You end up having greater stores of intramuscular triglycerides and glycogen. You see a decreased use of the anaerobic glycolysis system. And overall, that leads to an increase in AVO2. And lastly, we're going to look at the anaerobic training adaptations. So first of all, when we train anaerobically, so using resistance training or speed training, we see muscular hypertrophy occurring, and that's the enlargement of those fast twitch fibers. So, and that's why if you compare a sprinter versus a marathon runner, you actually see that the muscles are considerably different in size. We see an increase in muscle stores, the fuel stores, so we see an increase in ATP, PC, creatine, and glycogen. We see an increase in the glycolytic capacity, which basically means a greater ability to break apart glycogen. Cardiac hypertrophy, because the heart is a muscle. You can also put this inside as a muscular change. We see increased contractile proteins in the muscles, so that basically means that the muscle is able to contract at a faster rate more forcefully. We see increase in an enzyme called myosin ATPase, which is responsible for splitting ATP into ADP. So if we've got more of them, we see that ATP resynthesis can happen at a faster rate. We also see that there is an increase in strength of connective tissue. All right, so that's really important. So the muscle, it's not just the muscle getting stronger, but the connective tissue around it. We see an increase in the motor units. Therefore, we're going to have greater amounts of force production and the increased speed of nerve impulses and the muscle contraction speed. So more speed, more power. It's important to note that these changes are reversible once you stop training. So, but we're going to wrap it up there. I hope you've enjoyed this presentation.